back. Example 2. If a rod or a piece of wire is homogeneous, then its linear density is uniform and is defined by the mass per unit length. So rho, that's the Greek symbol RHO, rho. It stands for the sound R in English, right? R. So rho is M over L. So you see, homogeneous rod or piece of wire means what? Uniform width. Okay. Then its linear density. Density, as the name suggests, density is mass over length. Total mass over length. That's what it means. That's what density is. It is measured in kilograms per meter. Suppose, however, that the rod is not homogeneous, but that its mass measured from left end point to x is fx. So you have a function which gives you the mass for varying length of the wire or rod. Then the mass of the part of the rod that lies between x equals x1 and x equals x2 is given by delta m, that is f of x2 minus f of x1. So the average density is delta m over delta x, f of x2 minus f of x1 over x2 minus x1. Let's go back to the picture. Here is x1, here is x2. Your rod could be thick somewhere, thin somewhere, whatever. We don't know how it goes. So we measure from our starting point the mass of the rod, okay, for any x. So the mass of the rod from x1 to x2 you obtain by taking mass until x2, subtract mass until x1. So the difference in those masses is delta m, and the difference in those x's is delta x. That's all this is, delta m over delta x. So this is called average density. Average density is spoken over an interval of the length. Now suppose I let the denominator delta x go to 0. Delta x going to 0 means x2 is approaching x1. Then we are computing the average density over smaller and smaller intervals. The linear density rho at x1 is the limit of these average densities. Linear density, so that's the difference between average density and linear density. Linear density is the limit. So linear density is the rate of change of mass with respect to length. So you can imagine linear density is actually the derivative, okay, limit. So linear density is the derivative of the mass with respect to length. For example, so suppose you are told the function fx is square root x. Okay, then the average density for x going from 1 to 1.2 is f of 1.2 minus f1 over 1.2 minus 1, blah, blah, blah. You can find this. But what is the density, linear density? Well, you have to take the derivative with respect to x. I want to find linear density at x equals 1. Evaluate at x equals 1 the function for m. What was the function for m? Square root x. So derivative of square root x is 1 over 2 root x. Evaluated at x equals 1, you get this. So you see, average density over 1 to 1.2 is quite close to the linear density derivative. Alright, another example is the current. What is current? A current exists whenever electric charges move. So here is this figure, shows part of a wire and electrons moving through a plane surface. So when electrons move through that surface, that's when you see electricity is created, say. Delta x is the net charge that passes through this surface. So that's your surface, right? It's going through, charges are moving through this. Now, we are looking at a time period of delta t. average current is delta Q, that is the net charge, over change in time interval, Q2 minus Q1 over T2 minus T1. Whereas what is the current? Current is the limit. Okay, at any given time T1 is the limit. So current is the derivative as opposed to average current, which is slope of the secant. All right. Now we'll see some examples on chemistry. Well, next video we'll continue on example from chemistry. Until then.